All right, so let's take a look at our lesson for today. Today is Basic Derivative Rules, Day 2. Today's lesson is much more conceptual than yesterday's lesson. Yesterday's lesson we were learning derivative rules, you know, the power rule and all that kind of stuff. Today we're actually going to get more into the concepts of derivatives, which is pretty important. So first, let's look at the concept of a sketch. They want us to sketch the graph of a function f such that the first derivative is less than 0 for all x. Okay, that's the first criteria. So let's see. So we have the first derivative is less than 0, so it's negative. First derivative is negative for all x. And the rate of change of the function is increasing. Okay, so let's think about what that would mean. To have a negative slope, or basically for the derivative to be negative, means that we have to have a negative slope, right? We have to have a negative slope. And so, and then we want the rate of change. Now takes us back to that crazy question that we had on the homework that I have since fixed. I don't really know what happens when you go in and look at the homework for number 1 when I change the question, what you'll see. I'll be interested if you would tell me what happens, because your answer won't apply to the question that I put up there, so it'll just be kind of weird. But at any rate, I have fixed it. So let's talk about, we want the rate of change. It's talking about a specific value, rate of change. How do we designate rate of change? What number is that? It's the value of the derivative, right, at a point, the value of the derivative. So we're really looking at numbers here. We're not looking at speeding up or slowing down, which is conceptual, which involves many steps. We're just looking at numbers. We want all the numbers to be negative, first off, and we want, what I mean by negative, we want all the slopes to be negative, because that's what this is saying, and we want the numbers to increase. The rate of change is the number. We want it to increase. So we want it to go from, like, you know, negative 100 to, you know, increasing would be going right, to negative 10 to negative a half. You know, that's what we want it to do. Are you with me? So when lots of renditions, but one rendition would be, you know, we start out really high with a high negative number, like negative, I don't know, negative 100 or something. And then we keep going like this, and actually that would need to stay negative. So let's erase that little part. So that would give us, you know, anywhere I would draw a tangent line. Here, a tangent line would be, you know, pretty steep, like a negative, I don't know, negative 50 or something per slope. You know, here I draw a tangent line. It's less steep, so it's less negative. You know, maybe a negative 2. You know, and I keep all the tangent lines keep getting, the slopes of the tangent lines are increasing, but they're not going positive. Okay, so that would be an example of drawing a function, the actual function graph, where the derivative is negative for all x and the rate of change is increasing. So think of the rate of change as a number. You want the number to increase, the derivative number to increase. Okay, is that okay? All right, the next problem asks us, it's kind of similar to one we've done before. We actually were working on continuity, if you recall. When you would say, like, what's the value of, and there would be some letter in there, like A or C or K, something. What would the value of that be to make the function continuous? Do you remember those problems a week or so ago? Well, now we're adding a layer on. We need to find two variables, A and B, so that it's differentiable everywhere. Now, differentiability, there's two things for differentiability. First of all, does it have to be continuous to be differentiable? Yeah, we have to do the continuous part that we did before. We still have to do that step. We have to force those to be continuous. And we do it the same way. We would set them equal to each other at 2. Okay, and we'll get an equation. So that is also true. But now we have, is it possible to be non-differentiable and continuous? Yeah, right? We looked at that. It could be a corner or a cusp or a discontinuity. There could be something there well, it's continuous, it won't have discontinuity, but it could be continuous and not differentiable. So we also have a second step to do. We also have to make sure it's differentiable at 2. And the way that we do that is we take the derivative and we set the derivatives equal to each other at 2. Okay, so setting the position functions equal to each other at 2 basically helps provide security that it's continuous. And then setting the derivatives, first derivatives equal to each other at 2, provides that we are differentiable. Okay, so we have 2 steps. All right, so let's do that. So let's do the first step because we're used to that. To make sure it's continuous, we would set these equal to each other at x equals 2. Okay, that's where we are concerned with. So we would set them equal to each other at x equals 2. So I'm going to substitute a 2 in for x. So that would be what? 4a plus 1, 2b minus 3. Okay, that's my expression for continuity. That expression, if I can make that expression true, then I will guarantee that this is a continuous function, which it has to be differentiable. Step 2, I'm going to actually find the derivative of this. So f prime of x, remember the derivative of a piecewise is a piecewise. So let's see, let's take the derivative of the first piece. The derivative of a, we know that's just a number, a constant. We don't know what it is, but it's a number. Ax squared, so we do the power rule, 2ax to the first, right? And the derivative of 1 would be 0. And that piece works when x is less than or equal to 2. Now for the second piece, the derivative of the second piece, remembering that b, it represents a constant. It's just a number. So the derivative of the second piece would be b, and the derivative of negative 3 is 2. So it's just b at x is greater than 2. So there's our derivative. Now to ensure that it's differentiable, the derivative has to have the same value at 2. So I set them equal to each other. So 2ax equals b at x equals 2. Okay, that's the location that I want them to be the same. And so then I would substitute a 2 in for x. So that would give me, what, 4a equals b. And now what I have is I have 2 equations. I have this one and this one that I want to put in a system and solve. I have 2 equations. Okay? So it doesn't really matter which way we do it. Yeah, it makes no difference. So since I already have a 4a here and I have a 4a here, it'd kind of be convenient just to replace the 4a with the b. That would be one technique. Y'all okay with that? Yeah, just that's one way to do it. Of course, there's a ton. You can come up with whichever way you want. But this already has a 4a and so does that. So I'm going to go ahead and take this equation and replace this 4a with b. So b plus 1 equals 2b minus 3. So then I bring this b over and I get b, and I bring that over and I get 4. So I know b is 4. And so with that information, if b is 4, I can go back up to this expression. So 4a equals 4. So a is going to be 1. So my answer, find a and b. So we know a is equal to 1 and b is equal to 4. So we've solved that. Now we're continuous and differentiable. Okay? We good? All right, we have one more page. So let's go to our next slide. So here we have some graphs, and this is very conceptual. It's a very conceptual thing that we're doing here. So let's kind of concentrate on what we're doing. It tells us the graph of position function is shown. They want us to sketch the velocity function from 0 to 9. So in other words, they want us to read the derivative off of the position function and graph it. Okay? Read the derivative off of that function. Now, there's quite formal way that you could do it. I mean, you could find the equation of each of those lines, and you could take the derivative, You could, right? That's a technique. I'm not going to do it that way, but you can. If you found the equation of this line, let's think that through. An equation of a line is, one example, y equals mx plus b. Right? If you take the derivative of a line, what are you going to get? A number. You're going to get the slope, right? You're going to get a constant. So this is a really basic graph, which is really nice for us because we're able to find exactly what the derivative would be. And we don't even have to write the equations for each of the lines, because if we took the derivative of this equation of a line, we know we would just end up with m. You with me? Okay, so we just really need to find the slope of each segment. So we're looking here. So between here and here, so what is that? 0 and 4. Between 0 and 4, what's our rise? 1, 2, 3, 4, 5, 6. So the rise is 6 and run is 4. So basically, what, 3/2? And so I would go over here. Now, I'm drawing a graph of the derivative over here. Is the derivative going to exist at 0? Is it differentiable? No. Why not? It's not continuous. It's only right continuous, right? It's not left continuous. So I know I don't have a derivative here. But I need to go to 3/2 over here, and I need to put a hole there because there is no derivative value there. It doesn't exist. What about at 4? What about right here? Is the derivative going to exist right there? No, because it's a corner. Right? We learned about differentiability a few days ago. It doesn't exist at corners. So I need to carry this line to 4, but I can't let it equal at 4. So that is the first piece of my velocity function. All right, now let's look at this piece between 4 and 7. Okay, what's the slope of that piece? It's pretty straightforward, 0, right? And does the derivative exist at 4 or at 7? No, so I have to do holes there. So at 4 and 7, but in between there, the derivative exists. All right, and the last piece is from 7 to, let's see, they want us to go to 9. Well, just coincidentally, that's the end of the graph. So our slope would be rise would be 1 over run would be 2. Again, I think we have the pattern. We know that derivative isn't going to exist here because it's a corner. It's not going to exist here because it's not continuous. So we need holes there at 1/2. So here and here. There we go. And there's our velocity graph. Okay, questions about that?